Well, hello Year 11 and welcome to the second one in a series of key skills for AS Chemistry. Things that really you should have mastered at GCSE, but perhaps many of you didn't because either they weren't focused on or they were glossed over as part of the GCSE course. And today we're going to look at ionic compounds and ionic equations, because this is something that actually you were introduced back in Key Stage 3, even the very end of Key Stage 3 back in Year 9, the idea of how to work out the formulae of ionic compounds and the ions that go together into making them. And it's used throughout GCSE chemistry, but I still have Year 10 and 11 students and even Year 12 students who cannot work out what the formula of particular compounds are, how to work them out and how to take them apart again. So just to convince you that this is something that is there at GCSE, here's a GCSE question. Why does cobalt form different coloured compounds? Of course, the answer is that it is a transition metal. Remembering, of course, that transition metals form coloured compounds while group 1 and 2 compounds form white or grey compounds. But this is the interesting one. An oxide of cobalt has the formula CO2O3, so cobalt there, O3. Which cobalt ion is present in this oxide for 1 mark? Well, I'm hoping that you realise that this must be made up of cobalt ions of unknown charge and oxide ions, and you should remember that oxide ions have the charge 2-. So therefore 3 of those 3 oxide ions would have a total charge of 6-, which means the total charge of the 2 cobalt ions must be 6+, which means each one of those must be 3+. Now, it didn't occur very much at GCSE, but this sort of procedure occurs an awful lot at AS Chemistry, and it is assumed that you know how to do this. We're not really going to go through it from scratch. So here's some A-level questions, actually AS-level questions on this idea. So obviously a bit more complicated, looking at the charges on vanadium here. So the vanadium does not have an oxidation state. For your purposes, read charge of 3+ in which of these? Well, we hopefully know that water has charge 0, and there's 6 of them, so that's 6 times 0, so that's 0. The overall charge is 3+, so that must be V3+. Looking down here, something that you will learn at A-level, the C2O4 ion is a bit like a dicarboxylic acid with a charge of 2-. There's 3 of those, so the overall charge must be 6- of those. You've got a 3- charge overall, so the vanadium must be 3+. Here, hydroxide, OH-, that has a charge of -1. Water, we've said, has a charge of 0. So we've got 3 times 0, 3 times -1. The whole thing's neutral. So again, that must be V3+. Which means the one that must not have the charge of +3 is this. And again, we look at Cl. We realise that is a chloride ion. And there's 4 of them. So there's an overall charge of 4- from those. The whole thing has a charge of 3-. So the vanadium must here have a charge of 1+. Now, I'm not expecting you to be able to do this now, but what I am trying to show you is that you need to know the formula and charge of these ligands in order to be able to do that question. You need to know that OH is OH-, Cl is Cl-, and this is stuff that you should know from GCSE. Down here, oxidation numbers, we've got more examples. I'm not going to go through all of them, but let's have a look at, for example, the oxidation number of sulfur in S4O6 2-. Well, we know that oxygen is always O2- and that there are 6 of them, so that's an overall charge of 12-. We know that the whole thing has a charge of 2 minus, so that means that there must be a charge of 10 plus from the 4 sulfurs. And therefore that means each sulfur must have a charge of 2.5 plus on average. So A. Again, I'm not expecting you to be able to do this, but what I'm trying to do is show you how the stuff that you've done at GCSE, compare it back to this. If we have a look up here of the cobalt 203, that's very similar to that S4062- question we just did. So, let's review what we do know and what you should be familiar with. All group 1 elements like to make one bond. Why is that? Well, every single group 1 element has one electron in their outer shell that they like to get rid of. So all group 1 elements, be it sodium, potassium, rubidium, always form the 1 plus ion. Form one bond. Here we've got chloride. And all these elements like to also form one bond. Why? Well, we know that these elements have got one gap in their outer shell. So they want to accept one electron, and they all form negative ions like Cl-, Br-, I-, F-. Many students at GCSE get confused and say, oh, but sir, you always say that they're diatomic, Cl2, Br2, I2. Yes, as elements, as halogens, they are diatomic. That's how they fill their shell when they've got no other option. But if there's electrons available, then they can fill their shell in other ways, and so they don't need to be diatomic. When you've got therefore sodium and chlorine bonding together, sodium and its one outer electron can bond in a 1-to-1 ratio with chlorine by giving that one electron over to the gap in chlorine's shell. NaCl. Magnesium. And all group 2 elements, 2 electrons on the outer shell, which they want to lose, Mg2+, Ba2+, Be2+, they all form the 2+ ion. They form 2 bonds. Oxide, we've seen already. Oxygen, 2 gaps in that outer shell. Wants to accept 2 electrons. Forms O2-, S2-, Se2-. Bonds 1-to-1 with magnesium because the magnesium can get rid of its 2 outer electrons over to the 2 gaps in oxygen's shell. MgO. If the numbers don't match, sodium oxide. Again, let's go back here. Anything ending in "ide" means that there's 2 elements. There's a metal and there's a non-metal part. So sodium oxide is bonding between sodium and oxygen. Now sodium has got 1 electron in its outer shell. Oxygen needs 2 more. So sodium, one of them, cannot satisfy the oxygen. So what do? We need another electron that comes from another sodium with 1 electron in its outer shell. And that's why that is a 2-to-1 ratio, and it forms the formula Na2O. Magnesium chloride, again magnesium and chlorine. You need 2 chlorines. Why? Because magnesium has got 2 electrons in its outer shell. Chlorine will only accept 1 of them. It's only got 1 gap, it's in group 7. So magnesium's not happy unless it can get rid of both. So it needs a second chlorine with a second gap for that electron to go into MgCl2. You can do it with valency, you can do it with charges. Aluminium, 3 plus, nitrogen, 3 minus. Just to say, this N3 minus is nitride. Aluminium, nitride, simple formula, ALN. And you can begin to see how more complex matching happens. You can do this from the charges, of course. So exactly the same method is to say magnesium 2 plus, N3 minus. Rather than thinking about the number of bonds, we need the overall charge to be neutral. So all ionic compounds are neutral. So we need to somehow combine these ions to get a neutral compound, and the obvious way to do that is to have 3 of these, total charge 6 plus, 2 of those, total charge 6 minus. It's a neutral compound. You're doing exactly the same thing as you're doing with the valency. So you should, I'll go back here, you should be aware 1 plus, 2 plus, 3 plus, 1 minus, hidden under me, 1 minus, 2 minus, 3 minus. Okay, so what about group 4, groups 8 and the transition metals? Well, the first 2 you should definitely know, the last one possibly you're not sure. The answer is that group 4 rarely forms ionic compounds, although it does occasionally. You might have heard of things like tungsten carbide. And so that would be the C4 minus ion, and depending on what the charge tungsten has, obviously depends on the formula, but let's say the tungsten was 2 plus, W2 plus, C4 minus, then making that balance, you would have to have W2C for that. Group 0, well, we should know that these things don't form bonds. The noble gases don't form bonds. They've got full outer shells. They've got a charge of 0. Now, for the transition metals, you need to be a bit more on it at A level. The one thing you do need to know is you presume that the charge is 2 plus unless you're told otherwise. They're a metal, so it's going to be positive, right? For reasons that you will discover quite early on in your AS course, they will tend to form 2 plus ions. So unless you're told otherwise, assume it's 2 plus. For example, zinc is always the 2 plus ion, Zn2 plus. The exception, you do need to know this off by heart, silver forms the 1 plus ion, Ag plus. Many students don't bother to learn that, they come up unstuck. Otherwise, for things like iron, which commonly forms either the 2 plus oxidation state or the 3 plus oxidation state, so Fe2 plus or Fe3 plus, you are told what the charge is by the Roman numerals, and therefore you do need to know Roman numerals all the way up to 8. So for example, the manganese 8 ion. Okay, you do need to know your Roman numerals. And another example down there is copper 1 versus copper 2. Right, this is my bugbear from GCSE. I have told students repeatedly in every year, year 9, 10 and 11, they need to learn these, and they never do. You do need to know these off by heart and quickly when it comes to A level. At AS level, the only positive ion you need to worry about that behaves strangely, that behaves like a single entity, one group, doesn't split up, is the ammonium ion, NH4+. All the others are negative. The only positive ion, NH4+. Don't confuse it with ammonia, which is NH3. Okay, and you should be aware of that from C10. Ammonia being used to make ammonium salts with the Haber process in fertilizers. Hydroxide you should know, OH-. Nitrate you should know, NO3-. Carbonate, CO3 2-. Sulfate, SO4 2-. Phosphate, PO4 3-. If you see these, you never split them up. And that will become important later. So here's some practice. Have a go. What are the ions on the left? What is the formulae for these things on the right? Pause the video, have a think. Okay, so here are the answers. Check them yourself. A few to point out. Of course, we've got sulfide here, not sulfate. Make sure you didn't make that mistake. Telluride, you've probably never heard of it, but tellurium there, sitting under sulfur and oxygen in group 6, so 2-. Zinc, of course, as we said, is always 2+, presume 2+ unless you know better. Ammonium, the one that people always get wrong, NH4+. Tin 4, SN4+, hydrogen carbonate, HCO3-. Silver, of course, the exception, Ag+. Most of these should be fairly straightforward. Just be careful with your brackets. For example, iron 3 nitrate, Fe, brackets NO3, close brackets, another 3. Lots of people miss out one of those 3s. I often see Fe, brackets NO, close brackets 3 there, people being careless. Ammonium sulfate, NH4 in brackets 2, SO4, and calcium phosphate, CO3, open brackets PO4, close brackets 2. If you need help with any of those, email me directly, but I'll presume you did okay on those. So the reason we need to use this is because we need to be able to quickly write ionic equations and indeed fully balanced equations with no help. We need to be able to very quickly work out the formulae of those compounds. Let's remind ourselves, what is an ionic equation? Right, you should recognise this from C8. You take sodium chloride solution, Na plus Cl minus ions floating around in water, and you react them with silver nitrate solution. What you end up with is a precipitate of silver chloride, which is what colour? I'm really hoping you instantly told me white. In one of our later videos, we will be looking at what you need to remember from that horrendous analytical chemistry topic, but you do need to know a lot of it. So silver chloride forms a white precipitate, and we're left with sodium ions and nitrate ions in solution. So what you probably have noticed is actually some of these chemicals haven't reacted. So the sodium ions that were there at the start are unchanged. They've done nothing in this reaction. They're not part of the reaction. Ditto, the nitrate ions have done absolutely nothing. There's the nitrate ion sitting there at the beginning. There it is sitting at the end. It has just watched the reaction take place around it. It's not done anything. It's not part of it. It doesn't give electrons, take electrons, recombine. It sits there doing nothing. The real reaction is that the silver ions in solution have bonded with the chloride ions in solution to form a solid. And that's what's gone on there. And that is the ionic equation. That shows you what is really going on in the solution. Here's another one. Pause the video, have a think. Well, hopefully you realise that the nitrate ions are doing absolutely nothing. Ditto, the sodium ions are doing absolutely nothing. What is happening is that the lead ions in orange are interacting with the iodide ions in green and forming a solid. Here's another example. I'm going to put some iron into some copper sulfate solution, and after a while I end up with iron sulfate solution and copper. What's going on? Pause the video, see if you can write that ionic equation. Well, again, what I hope you realised is that the sulfate ions have done nothing. And that's it, actually. The copper ions have gone from being copper ions to being copper atoms. They have lost, they have gained electrons. They've lost their charge, but they've gained electrons. In other words, oil rig, they have been reduced. The iron atoms, which were neutral, are now iron ions. They have lost electrons. They have been oxidized. So the reaction is clearly between those things. Iron atoms have become iron ions. Copper ions have become copper atoms. So copper ions and iron atoms have become iron ions and copper atoms. In other words, this shows us that real reaction is copper and iron exchanging electrons. So how do we work out the ionic equation? You start with the word equation. So iron and copper 2 sulfate, copper metal, iron 2 sulfate. And this is why you need to be able to do it, because you need to be quickly able to write out what the balanced chemical equation is involving state symbols. So iron, Fe, solid. Copper metal, copper, solid. Copper 2 sulfate, iron 2 sulfate. No longer is this worth a mark by itself. It's part of a bigger question. You just need to be able to know the formulae of those things. You also need to be able to recognise that this and this are made up of ions. We need to split up those chemicals. As I've said here, and this is something I'm trying to hammer home with my year 10s, now comes the tricky bit. We have to decide whether any of the chemicals aren't really what they say they are. Huh? What does that mean? Let's have a look. Well, this is my usual suspects here. The 5 suspects in the film The Usual Suspects. One of them is not who they say they are. Who is it? You'll have to watch the film to find out. But one of these is actually something slightly different. Put a metal into water, nothing. A lump of metal, a lump of aluminium being put into water is still a lump of aluminium. That is exactly what it says it is. Aluminium solid, I dunk it in water, it's still aluminium solid. Yes, some things react with water, but they don't change state when they're in water. If I take a molecule like bromine, Br2, and I dissolve that in water, well, yeah, it's in water, but it's still just Br2. It is what it says. It's no different. Bromine liquid has become bromine aqueous, but actually it is still Br2. It may be a bit more social, hanging around with all the solvent molecules at the party, but it's still the same guy underneath. If two things are tied together, like lead iodide, PbI2. We put lead iodide in water, it stays as solid lead iodide. The compound remains bound together. The ions remain bound together. If the equation says lead iodide, it is lead iodide. Does exactly what it says on the tin, as Ron Seal would approve. Okay, so we're looking for chemicals that aren't really what they say they are. Metals are metals, covalent molecules are covalent molecules, insoluble precipitates are just really insoluble precipitates. What isn't what it says it is? Sodium chloride, copper sulfate, potassium hydroxide, calcium nitrate. Why? Why aren't they what they say they are? Well, here's the thing. Sodium chloride, solid, is that. It is a lump of sodium chloride. When it's in solution, NaClAq, can you see a single sodium chloride particle there? I can't. What I see are chloride ions and sodium ions. Actually, two completely different chemicals. It has become sodium and chloride. It is different things. So here's my example. Iron and copper sulfate, iron sulfate and copper. Iron is just that. It's iron. We don't do anything with it. We don't do anything with the copper. But these things, copper sulfate is copper and sulfate. Iron sulfate is iron and sulfate. So we split those up. And this is why we need to know the ions. We need to know that copper is 2+. Sulfate doesn't get split up, is SO4 2-. From this formula, we can tell that iron must be 2+. Why? Because the whole thing must be neutral. And we know of the back of our hands. Who knows the back of their hands? I don't. It's an expression. But if sulfate is 2-, which we know off by heart, then that means over here the iron must be 2+. Once we've done that, we're laughing. Sulfate, sulfate, it's exactly the same on both sides. We cross that out. They are the spectator ions. They watch the reaction. We remove them from the equation and we get the final ionic equation. State symbols are a must with ionic equations. Must. You must put them in. The real reaction, as we've already said, is when iron gives 2 electrons to a copper atom. Iron is oxidized, copper is reduced. Here's a go, see how far you get. Here's the word equation. Can you write the balanced chemical equation with state symbols and then the ionic equation? Okay, here's the balanced chemical equation. I'm not going to tell you how to work out the formula of potassium bromide and potassium chloride. You should know how to do that. Chlorine and bromine, remember, they're both diatomics if they're an element. What do we split up? Well, chlorine is covalent. It doesn't split up. It is a Cl2 molecule even, well, as a gas state. Bromine, perhaps even more confusingly, but it is still a Br2 molecule in water. It hasn't split up. It is Br2. But the potassium bromide, the potassium chloride have split up. Potassium's the spectator ions. They do nothing. So the final ionic equation is this. Chlorine and bromide gives chloride and bromine. In other words, the real reaction occurs when chlorine gas steals 2 electrons from bromide ions. Chlorine is reduced, bromine is oxidized. Final example, have a go at this yourself. Copper 2 chloride solution, sodium hydroxide solution forms sodium chloride solution and copper 2 hydroxide solid. This is one of your tests from C8. Can you write the ionic equation? Well, hopefully you were able to write the chemical formulae. This is where we need to be a bit careful. So when we separate the ionic compounds, of course, because there were 2 NaOHs, Na plus OH minus, Na plus OH minus, of course that means there's 2 Nas, 2 OHs, ditto 2 sodiums, 2 chlorides. If you forget those, you might run into trouble. If you haven't balanced your equation first, you might run into trouble. But looking at this, we can see that copper hydroxide is insoluble. We don't touch it. The sodium are spectator ions. The chlorides are spectator ions. And so our final ionic equation, a copper 2+ ion bumps into 2 hydroxide anions to form solid copper hydroxide. The real reaction occurring when a copper ion meets 2 hydroxide ions and they combine to form an insoluble precipitate. The sodium, the chloride, that's a red herring. They're not part of the real chemical reaction. Right, have a go at this. What ions are there in these chemicals? Have a go, pause the video, restart when ready. Okay, so sodium chloride, obviously sodium plus and Cl minus, aluminium nitrate, Al3 plus and 3 nitrate anions, each with a single minus charge. It's fine if you want to write 3 NO3 minus, that's not a problem. H2SO4, sulfuric acid, 2H pluses, SO4 2 minus. Bromine, covalent, 2 non-metals, no ions. K2SO4, 2K pluses, SO4 2 minus. Fe2O3, well, we need the information from the oxygens to work out what the charge on the ions are, but they are Fe3 plus ions, 2 of those. Methane, you should instantly recognise it. No ions, it's a covalent molecule. H3PO4, phosphoric acid. I should point out, just in case you haven't worked this out, if hydrogen is ever at the start of the molecule, with one notable exception which we're going to get to, then it is acting as a metal, and therefore it's almost certainly an ionic compound. Barium hydroxide, Ba2 plus and 2 OH minuses. H2O, this is the exception. Yes, I know we tell you at GCSE that it splits up to give H plus and OH minus, but this is about 1 in 6 million molecules. So once you've written H2O 6 million times, then by all means write it as H plus and OH minus, but only on the 6 millionth go. Zinc sulfide, not sulfate, sulfide, Zn2 plus S2 minus, NH4 3N, N3 minus, 3 NH4 pluses. Hopefully you recognise the hydrogen carbonate ion, HCO3 minus. Don't pull that apart, it's not H plus and CO3 2 minus, HCO3 minus, hydrogen carbonate. Ammonia, no ions. Again here, manganate, manganese trioxide, not manganate, manganese trioxide. We need the oxygens to tell us that it must be Mn6 plus. SO3, looking down here, well, sulfur is a non-metal, oxygen is a non-metal, so these are all non-metals, so it must be covalent. There are no ions there. Hopefully you got most of those right. Finally, let's have a look. So these are some A-level questions. This is the sort of thing. Now again, remember these are 1 mark, 1 minute. This is why you've got to be quick. So essentially you are trying to work out the ionic equation in 1 minute for one of these reactions. So I'm going to do question 44 and 46. I'll leave you to have a look at 45 and 47, but let's have a look at those. When 1.270 grams of copper is added to excess silver nitrate solution, 4.316 grams of silver forms. The ionic equation is what? Now, Ag2 plus. I know that's wrong. So it's definitely not B or C because they have an Ag2 plus ion. Let's have a look. Copper 1, copper 2 plus. Okay, it could be A or D. At this point, I could presume that, unless told otherwise, copper is 2 plus and go for A. But actually, to really work it out, I am going to use my maths. So moles of copper, 1.270 divided by 63.5 gives, where's my calculator gone? 0.02. And moles of silver is 4.316 divided by 107.9, which equals 4.316 divided by 107.9 gives 0.004. 0.04, sorry. So that is 1 to 2, 1 copper to 2 silvers. So it must have been A, which actually we could have presumed by assuming that copper was 2 plus. But we know that silver is always 1 plus, so it couldn't have been B or C. Down here, reaction of nickel 2 carbonate and hydrochloric acid. Okay, let's have a look. Well, we know that for the ionic equation we're not going to touch a covalent molecule, so it's got to have H2O in the right hand side, so instantly B and C are wrong. We know we're not going to touch this covalent molecule, carbon dioxide. That must be in the ionic equation. So we've limited ourselves to A and D already. Now, when I look at this, I also notice HCl here. HCl aqueous. I know that is split up into 2 H plus ions and 2 Cl minus ions in reality, so that can't be right. So therefore the answer must, by just understanding how to do ionic equations, the answer must be A. So nickel carbonate solid plus 2 protons gives nickel 2 plus carbon dioxide plus water. So actually you're not having to work out the full ionic equation here. you're using your sense of, I know I'm not going to touch the carbon dioxide in the water, so I can eliminate B and C. I know that HCl should be split up, so I'm eliminating D. And this is what AS level questions and A level questions expect you to do, is just know the procedures fast and quick enough that you can find the shortcuts to answer these questions. Again, I hope that was informative. If you do have any questions, please email me a.nixon@ulstergs.com. I got loads of great feedback after the first video, so thank you for that. Positive feedback, very welcome. Constructive criticisms also. And I will see you in another 2 weeks for the third video. Thank you very much.